to the organizers for giving me the opportunity to speak here in Shanghai. I was here once. Last time it was raining. Today it's raining, so I hope it's not my fault. But it's always very nice to see this very vibrant city, and so I'm very curious also to learn what's going on here scientifically. So today I want to give a talk that is a bit more a didactical overview talk of what we're doing in Erlangen about quantum key distribution. And I want to talk about things that also have to do a bit more with the practical side, and also some concepts that I would like to introduce. So, speaking of Erlangen, just to glimpse where I'm coming from. So, I'm coming from the Max Planck Institute for the Science of Light in Erlangen. That's a fairly new institute, it was founded in 2009. And just for you who wonder where Erlangen is, it's basically, this is Germany, and so it's in southern Germany, it's Bavaria. And I thought, what's the typical cultural thing we have in Bavaria? I thought about the beer that we have. Every village has its brewery, so that's kind of, this very special thing here. So the institute has several divisions, all concerned about light and dealing with light and photonics. So I'm in the division of Gerd Leux, and I'm leading the quantum information processing group in there. We're dealing with all sorts of quantum optics, quantum information, mainly around continuous variables in quantum optics. So I want to talk about two topics today. One is dealing with the continuous variable fiber, QKD, and I'm very happy about this very nice talk that was given before about continuous variable QKD, so I don't need to introduce all the basics there. Now what I wanted to talk about today is about the concepts that you can take there, really to take this to a very high speed case. And what I think is very nice there, that is you can learn from what classical telecom people have done. We had some projects some years ago together with Bell Germany about quantum receivers and how is all this, and telecom, and then the channel capacity and so on. And when talking to these people, you learn a lot. So these engineers really know how to get the technical possible out of the systems. And so it also helps a bit to look at history. And if you look at classical telecommunication, people, what really boosted it was optical telecommunication over fiber networks. And then for a long time, people used amplitude modulation or some variation of that and so on. Though knowing that coherent communication with phase space in principle would be much better to use. By the way, when I prepared a lecture, I once Googled when was the first coherent laser communication link established, and I was quite shocked when I saw what came out, because Google showed me a declassified military document from 1962. Just a few months after the invention of the laser, they did coherent laser communication, and they even calculated the channel capacity with the shot noise of the laser. That's quite interesting. So you get quite modest if you read that. So the reason why coherent communication was not confirmed for a long time was that people were really concerned about, oh, you have to deal with this reference phase, the local oscillator and all this. And this is complicated, you have to do active feedback and so on. Until recently, 10, 15 years ago, so if you look at the high secret key rate, we saw very nice results before, but there it's really also about the detection. So you need a very high speed photodetectors. And it's not so easy to get high-speed detectors that at the same time have a very good behavior and signal-to-noise ratio, quantum efficiency, and so on. You want to be compatible with telecom networks. There's also very nice results there. So you want to really be able to get into this wavelength division multiplexing network and be stable. Don't disturb other channels, don't get disturbed by other channels, and so on. People looked a lot into those things. And you also want to be resistance against some adverse effects like noise that can happen in the channel, and some fluctuations or finite size effects. And when I was talking with my students, we thought about going up in speed, And I thought, maybe, I mean, just going up in speed sounds a bit boring, right? I mean, it's more like a technical thing. But what we found out then is just by going up in speed, you can really solve a lot of problems. Because actually, like in this classical telecommunication problem, you freeze out a lot of problems. So all those phase drifts, all those noise things, they are semi-static if you have very, very high speed measurements. At the same time, you don't have to care about local oscillator phase drifts and so on, the frequency of the local oscillator, because also there, it's really so slow compared to your measurement speed that you can neglect it. Same for finite size effects. If you start with much more raw speed, this also helps you. If you look in the classical telecommunication schemes, they usually use some quadrature encoding in phase space. So it's just really, or we can see this as coherent states encoded in phase space. And so what we tried really is to go into this direction and to really kind of mimic what they're really doing in classical telecommunication. And if you then do this, and if you look at that, I mean, what are we doing? What we usually then try to do is do some heterodyne detection. That means we measure the Q function of the whole systems, X and P at the same time. And if we do this with a heterodyne detection, a local oscillator, and this local oscillator can be really local to your receiver, and then you receive some overlapping coherent states in phase space. That's what a continuous variable QKD is about. And now, some things got messed up, okay. Right, but now, if you want to do this heterodyne detection, I mean, of course, how these things behave in phase space really depends on the exponential parameters, like as we saw before. I mean, you want to have the same frequency, approximately the same frequency, and so on, and drifts and bandwidth. Now, if you do this with a rather slow system, this is what happens, right? I mean, you get the frequency drift, you've got a beating signal, and so the whole phase space rotates, and if you're not measuring fast enough, it's very, very hard to do something with that data. Now, if you go instead to speeds that is usually used in telecommunication systems like 10 gigahertz, then what happens basically is that the whole thing just gets frozen out. And it will rotate, that's the heterodyne beat. It's just your offset of frequencies, so to say. But if you measure fast enough, you can follow this rotation. And if you have, I mean, this is what you then use in data processing, and then it can just remedy the situation. You just rotate your phase space and you're fine again. This is what the classical guys are doing, and this is also what you can do in the quantum case. So to do this, of course, you need some reference pulses. So you need to send along some reference pulses that you can estimate how your phase drift is. But this is something which is much less worse than sending the local oscillator along concerning scattering and so on. So we had a look at that. How does that really work in practice? So we set up an experiment, and really kind of the standard way how you would do it, also like classical guys would do it. So we really used telecom components like a signal laser. We had a 10 gigahertz modulator, attenuation, and so on. And we have a DVDM channel, 20 kilometer fibers. And then we, in the receiving side, we really used those telecom components like, you know, a 90 degrees hybrid or fiber integrated and so on to measure the system. To make it a bit more realistic, we also put in another DVDM channel just next to the quantum channel and put 0.5 milliwatt of power into that channel and saw how it will behave to really kind of test this behavior. So just as an overview, this is how approximately you could compare it. I mean, in coherent telecom, you've got a sender, you've got a channel, you've got a receiver, and here in coherent telecom, classical telecom, you have your laser, phase modulation, and so on, WDM channels. You've got your local oscillator, so to say, the receiver side, the hybrid, and so on. In the standard continuous variable QQD, I would call it before, often you would do it a bit differently, sending the local oscillator along, which will generate some problems. You do this a bit differently, not all fiber integrated. And now with that concept, what you would do is really follow the telecommunication approach, make it as similar as possible, and reuse the components that they always use. Now, we did show some first results on the channel. Now, one thing, if you follow this kind of this approach in telecom, and you have those discrete modulation phase space, so the security proofs and continuous variable QQD still have to improve to give you a finite size key. There are some security proofs, but those security proofs are in a parameter regime that are still not really useful for the practical range. So I know people are working on that, and that's kind of one of those cases where the experiment is a bit faster than the theory, which not often happens, right? So that's just one word to the theorists out there. It's really worth going into that direction and invest some work in there. I understand that Gaussian states are much easier to handle than non-Gaussian states, but still, I mean, it's worth the trouble. So what you still can do so far is that you look at the channel and you look whether the channel is a quantum channel, whether it is entanglement breaking or not. I mean, if you do security proofs, you always rely on transferring the problem into an entanglement problem, even if it's a prepared measure scheme. And so there's this concept of effective entanglement or virtual entanglement, where you can transfer really this problem into an entanglement problem and see whether your quantum channel, like a fiber or something else, is really preserving the quantum correlations. And this is what we looked at. And basically here really the idea is, I mean, if you look at it and you look at an entanglement-based scheme, you have Alice and Bob. Alice has some states, Bob has some states, and you can treat it as some entanglement source in the middle. And if you just look at Bob, for Bob it does not make a difference whether you're in a setting where you have this entanglement, a real entanglement, or whether Bob sees just something from a prepare and measure scheme, because Bob can't really tell. So you can transfer this prepare and measure scheme to an entanglement scheme, and then you can, just by looking at the statistics of the data, you can transfer it into a problem which we can then call effective entanglement and characterize the channel. And this is what we did in the very first experiment. So that's basically our device here, putting into a 19-inch rack to operate on the channel. That's one of those histograms that we measured from the states, overlapping states, and we really followed this technique of going very high speed. There's 10 gigahertz modulation and detection that we did here with those reference pulses, some of the reference pulses, and then the quantum pulses that came. And we did two configurations. One is where we just looked at back-to-back, whether all this technique at high speed worked. The other configuration is that we put 20 kilometers fiber in between, and we really put half a milliwatt of power in the DVDM channel just next to the quantum channel. And in both cases, we see that we still have a quantum channel, so we can measure and quantify effective entanglement. So as a next step, of course, we then want to try a QQD protocol that delivering a final a quantum key, a final key. An alternative to QPSK or BPSK modulation would be to use Gaussian states for that security proofs exist, and it should also work with that regime. So the message is going to this other approach, kind of learning from the classical telecom, going really high speed. It's possible really to construct a quantum channel, a quantum communication scheme. So the excess noise that we saw here is not more than what we had in our standard scheme before. So that works pretty nice. Okay, so with that, I want to come something that is related but different, going from fiber to free space as an alternative. And we also heard a lot of very nice talks about that so far. So in free space quantum communication, I mean, the setting is similar like in fiber, though I mean, in the technical level, it's different because, I mean, in the free space link means that you have other noise sources. You have a lot of turbulence in the atmosphere that you have to deal with. You have absorption, not so much as in the fiber necessarily, depending on the wavelength, but still it might be there. And of course, the question is, how can you deal with that in the best case in the continuous variable machine? So let me say a word about the difference between a continuous variable and discrete variables as I see it. If you use continuous variables, I mean, basically what you do in the measurement process, it's an interference measurement. I mean, heterodyne, homodyne measurement is an interference measurement. So you take a local oscillator and look at your state. And the point is that every measurement that you do will deliver a result. Whereas in discrete variables, if you use a single click detector, sometimes you have a click, sometimes you don't have a click. So that's a difference. On the technical level, homodyne detection can be very high speed. We saw this before, and it can be 10 gigahertz or higher. And a very good advantage in free space communication is that this interference of the local oscillator defines your mode that you measure. And usually if you take a single click detector, it sees all the light, also scattered light, also scattered photons. So if you would do the experiments at daylight, it's very, very hard. You have to do very complex filtering mechanisms to really not get killed by all the counts of the daylight scattered photons. Whereas in homodyne detection, you only see that mode with a K vector that matches your local oscillator mode. And that means you're immune to all this gray light that might hurt you. What's the disadvantage, or why is the discrete variable protocols, why are they working so nicely over very long distances? And one reasons for that is that I see it like that in discrete variables there's some kind of intrinsic post-selection. If some photon gets lost, you don't detect it, right? And whereas in continuous variables, you always detect something, and you have to do this with error correction. So I think there's no principal difference in physics, but in the technicality of error correction and post-processing, there is a difference. And this makes the difference in the reachable rates so far. However, I believe this might change with increasing theory capabilities and error correction and post-processing capabilities. So I think there's a lot of interesting things that can still be done there. Now, what we set up is a transmission of continuous variable states through the atmosphere. Now you might think, oh, this is a bit, strange because, I mean, continuous variable, you have this phase space, that's amplitude and phase, and there's all those phase fluctuations in the atmosphere, and that's very hard to come by, right? I mean, you have completely distorted wavefronts coming out. And, well, one trick to remedy the situation is just to do polarization encoding, because polarization is very stable in the atmosphere, and the atmosphere is known not to be birefringent, apart from some ice clouds or so that might happen if you're unlucky. But otherwise, it's very stable for polarization. So what we actually do is we encode in polarization, and we do this in the continuous variable. And you can also do this. There are those quantum Stokes operators that describe the polarization state. And polarization is usually described on the Poincare sphere. So you have a Poincare space with those operators or the parameters. And for example, here on the top there's circular polarized light. Here on the equator there's linear polarized light, and so on. Now, what we do is we send the local oscillator along to our quantum states. And if you regard that in the polarization space, it's like you have a very bright local oscillator, and our quantum signal is tiny modulations on top of the sphere. So if you zoom in, locally it's a flat space, and you have these tiny modulations in this flat space. That's really locally, in a very, very good approximation. This polarization encoding is the same as standard XP phase space, the Heisenberg-1 space that we know. Okay, so we had some history in Erlangen, and did some experiments there. So, about a long time ago, we started in the lab. We did some free space experiments on the top, the roof of our building. Then we went a bit further to another building, 1.6 kilometers. And last year, we started some measurements really going a bit longer, Tenerife on the ESA, next to the ESA ground station. And I will tell you a bit later about a longer measurement from a satellite. Now, on the roof of our building, we have kind of an infrastructure to transmit our quantum states, the free space link. So we have a sender, Alice, on the roof. Then we have 1.6 kilometer link from the institute building to a university building. This is how it looks. If we look into the laser beam, we shouldn't do that, but the camera did it for us. The point is, it's not so long, but it's very turbulent because it goes. It's as bad as you can do it. There's highways, there's chimneys, there's everything in between. So it's kind of a nice channel to characterize your free space transmission. And so we really do this point-to-point link with polarization multiplex, polarization encoding. So we have a state preparation at the sender. So we just prepare our polarization states. And for QKD, it's a continuous rubber QKD, it's enough to use coherent states. So we do that and encode that in polarization. Then we go via the channel, and then we really do the same. We just do a polarization measurements on this side. So that again is a Q function measurement in polarization variables. And if we do that, there's one caveat, of course, and everything is fluctuating, right? You have a fluctuating channel. That means also your total power is fluctuating. And continuous variable, it's very important to look at your shot noise unit and to calibrate your system. And this, of course, changes when your local oscillator also gets changed, which you transmit. So what you have to do is really, you have this histogram of transmissions that can happen, and you have to do a binning. You have to divide your channel in virtual subchannels depending on the transmission that you have right now. And you have to do, and that's also, I missed out the reference here, but that's also what you have to put into security-proof considerations, which we did in collaboration with Vlad Uzenko from Olomouc. Now this is how the beam looks like. It's pretty much distorted. The wavefront is completely distorted. But the good thing is the polarization state is kept intact. So that's very nice. You can work with that. And that's basically how the transmitted Q function of the signal states looked like that we tested. We had a Q base K signal, continuous variable signal, and that's kind of the receiving Q function then that we measured, and we also could prove that actually it's a quantum channel preserving effective entanglement of the channel. Now, the question was, can you also do the same with a very fragile state, like a quantum squeezed state? And so we set up an experiment where we built a squeezer. So that's our portable squeezer. So we use a photonic crystal fiber that is pumped by femtosecond pulses. We use the kernel linearity to generate squeeze states. And we put this up to our roof and transmitted the state. And the nice thing that it really worked. So this polarization encoding is stable enough that actually we could reconstruct the Wigner function of the squeezed state at the receiving side. And that Wigner function really allowed us to characterize the state, and we could prove that the squeezing survives and the system is stable enough. Even all those fluctuations are in there. But that's the good thing. Polarization really doesn't care about that. Now, how about longer distances? So there is quite some race right now to look into space and into possibilities in space. Now, we heard on Monday that there's some very, very, very nice activities going on to generate new satellites to test quantum mechanics and the abilities to do with quantum mechanics. Now we thought we went a different approach. So instead of building a new satellite, we thought about kind of misusing something that is already in orbit. So if you look at all those missions that are envisioned right now, and really kind of up to starting right now, there's a lot of nice things going on. I mean, we heard about the endeavors in China. I mean, that's quite fascinating. I think that is something that is really dedicated to matter quantum states. But there's also a lot of other missions going on that have the goal really to test quantum mechanics, to test quantum channels and so on. I mean, we heard about the endeavors in Italy, and there's a lot of things going on worldwide. Now, there is already a satellite up in orbit that is using coherent optical communication. And that's a European satellite. Actually, that's many satellites. It's a European data relay system. And that was put up there because there's a lot of Earth observatory satellites, LEO satellites. They're very low Earth orbiting. They make pictures and so on. And the problem is you don't have enough bandwidth to bring down the data from a LEO satellite because it just is very quickly vanishes over the horizon, so there's not much time to get the data around. And so up in space, there's some geostationary satellites that act as a backbone. So the LEO satellite then does a laser link to the geostationary satellite and transmits the data, and then the geostationary satellite has all the time in the world to make a microwave link down to the Earth again. So this is established technology that is up there already flying, and it is using optical coherent communication. And that's exactly the technology that is very close to what we are using in continuous variable QKD. So when working with that company, we realized that the system they have is really, really very close to what we use. So the idea is, if you use those kind of satellite QPD, you would have a trusted satellite relay that distributes the keys, and then you have some metropolitan networks. Already now there are some existing quantum networks, also here in China, that then can again distribute the keys. Now this is one of those pictures of this European relay data system, and that's the laser communication terminal that company TZ Spacecom is using. We're collaborating with that, and that really uses BPSK homodyne technology. And that's, as I showed before in the fiber case, that's really close to what we are doing. I mean, this is basically what classical BPSK is. You have two states, two coherent states, minus alpha plus alpha, and this is what you do in continuous variable QPD. So it's just different parameters, if you want so. So this is how the kind of spots look like. If you have geostationary satellites, you could distribute really to very distant spaces. And now one of the colleagues calculated the total cost of ownership of really distributing keys with that system that already is partly developed. And the result is really surprising. So if you look at all the total cost of ownership, having satellites starting and so on, if you take this technology that is already there, you end up with costs that are per euro cents per kilobit secure key. And I think that's not so much for what you really want to use at the end. Now, this is something I show now the first time on a conference, and I'm happy to show this here in China, especially. What we did the last month, so we did the first measurement of one of those EDRS satellites, so it's a geostationary satellite, and we did a measurement from that geostationary satellite on the ground station in Tenerife that receives those satellites. And what we could prove is that really the states that are measured are really quantum limited. So we had a quantum limited measurement of the states in space, originating really from this geostationary orbit 38,000 kilometers ago, far away. So what we're currently doing is we are quantifying all the behavior of the quantum channels and so on, And it's quite interesting to see that all this atmospheric fluctuations in all the atmosphere does not really hurt this quantum state transmission. Just as a glimpse, I mean, this satellite is so far away that actually the general relativistic redshift is already larger than the laser bandwidth. So that also would lead to some opportunities really to test things in that direction. So yeah, to sum up, just kind of a message in fiber QKD, one can learn a lot from classical telecom, free space quantum communication. I think the message is really going, for example, to satellite QKD would be really economical. It's not something completely out of scope and expensive. So I think that's really a realistic way to go. So yeah, with that, I want to thank my group, and especially Imran Khan, who was leading the fiber project, and Dominic Elzer, who's not in the picture, who's leading the satellite project. And I want to thank you for listening.
All right, so the room is open for discussion.
Interesting talk. And the first question will be the gigahertz fiber classical fiber QKD, and what's the key rate, secure key rate?
Yeah, that's what I said. I mean, we did not test this right now, because for the QPSK or for the discrete modulation, we are still waiting for the security proof to do this. I mean, kind of we know how to do it, also concerning post-processing or so, but we need the security proof. So the next step we would do is also to try Gaussian modulation, and then I can tell you the key rate. The problem is this effective entanglement that we can prove shows that it's a quantum channel, but the function between effective entanglement and final key rate is non-linear, so it's not easy to kind of estimate what the key rate is.
But the second question is about satellite. So you, just like you send some coherent laser to the satellite, and there's a mirror or retroreflector to reflect the light back, and then you measure the light. Oh, it's
no.
A signal from the
So the satellite has a laser on it, which modulates the states, generates the states. That's the nice thing, because the satellite is built to do optical coherent communication. So it has everything on the satellite for doing that.
Okay, and then you measure
we measure the light from the state that is generated on the satellite and transferring to the ground station.
Yeah, but you mentioned that when you are doing the free space experiment, okay, the polarization doesn't change too much, but the spatial mode changes, right?
So this system uses phase encoding, so it's not polarization encoding.
So if it's spatial encoding, then if you want to do the homodynamic detection, those things is
so these systems, they have some active control of the waveform.
Okay, active control. You're talking about some adaptive optics.
Yeah.
Okay. Cool.
How much optical loss will you have between the satellite and ground? Is this a hindrance for continuous variable communication?
This is what Dominic looked into also in the studies, in the feasibility studies, with final key costs, so to say. And this depends on the aperture and ground, of course. So, but he did an evaluation of that with the aperture on space and ground. And if you do have a ground station with approximately a meter or so, which exists, then you're in the regime where you can do decoy protocols. That means a bit more than 50 dB.
50?
50, yes.
Just a small question for the coherent receivers that you used in both experiments, the 10 GHz fiber experiment and in your quantum limited, short noise limited coherent detection for the satellite. So how do these behave, these coherent receivers? What is the trade-off between bandwidth, electronic noise, and this type of thing?
For the satellite receiver, we've got an NDA with the company, so I cannot tell everything. I feel a bit stupid, but that's how it is in satellite business. But for the receiver, for the fiber case, I can tell you the bandwidth is a 20 gigahertz 3dB limit, and the clearance depends a little bit, of course, on how you max it out with the local oscillator. But we run it currently about 6 dB clearance or so.
More questions? Okay, if this is not the case, then let's thank Christoph once more. All right, so we have a bit of information now, so please listen carefully. So first, there will be a group photo.